So looking at this screen over here, you can see it says welcome to this lesson on parabolas. Drag the blue handles below to change the shape of the parabola. So if I basically go to these blue handles over here, you can see I can change the shape of the parabola. Parabola will be a smiley face, and sometimes it can be a sad face. And this over here is a turning point. You can see as the turning point moves, we can increase and decrease the steepness. We can stretch the graph horizontally, and we can also flip it over like that. But that's the turning point over there. So just an idea of the parabola and what it is. Previously, we focused on linear graphs, and linear graphs is any graph that has the shape of a straight line. A parabola is an example of a non-linear graph because it has a curved shape. So we have our exponential curve, which goes like this. And we have our parabola, which is your curve shape, and that's what we're going to be doing today. And you have your circle, and you have a cuttlefish. Okay, so we don't really have to worry about the cuttlefish. Now, you can see a parabola has a sort of U shape. You can see in many places in nature and architecture, from the flight path of a diabola to the tail, the curled tail of a squirrel. All right, you can see it's got a shape of some kind of parabola. Okay, but they do exist in the world a lot. In Desmos, we can plot the parabola using a formula, and in this case, y equals x squared would be the function of this, because we're saying that in the Cartesian plane, the vertex is the point where the parabola has the lowest y value. The vertex of the parabola has the coordinate 0, 0, and if we have y equals x squared, we provide x values, and we square it, we'll end up with y values. It's maybe not exactly y equals x squared, but just to give you an idea, this is how it looks on the Cartesian plane. This parabola is going through a vertex of 0, 0. Now, vertex is another name for a vertex is the turning point, and that's where the parabola would turn. There's an x and a y value that represents the coordinate of a turning point of a parabola. The vertex of a reflected parabola is the uppermost point. And there's the vertex. In this case, we're saying we have a reflected parabola where the parabola is going downwards. We're saying it's a sad-shaped graph, right? It's a sad-shaped parabola. And this parabola turns, it reaches its maximum point at the y value 4 and at the x value -3. So we have -3 and 4 as a coordinate of this over here. While we're on a Cartesian plane, let's also check out the x-intercepts of the graph. These are points where the curve of the parabola crosses or intersects the x-axis. The following graph intersects the x-axis at -2, 0, and 2 and 0. So if I drag this purple point below to change the x-intercept, you can sort of see as the x-intercepts change, we have some kind of symmetry in our graph. The distance from the center to the first x-intercept is -3, and to the second one on the right hand side is 3. And as I bring it in, you can see those numbers stay the same. -1, 1, -1.5, 1.5, -2, 2. Because there's some kind of symmetry as well involved in parabolas. You can draw a line through the center which would create that. You can draw a parabola by plotting points on a Cartesian plane and then joining them up with a smooth curve. Okay, so it says here, let's try a quick quiz. Then you can have a go at drawing parabolas. They don't have to be perfect. It's hard to draw a curve, but if you show specific points in the parabola, you can sort of get the idea of how to get this. And you can see the points have to be the same distance from the center. So we plot the points, and you can see if you draw a line through it, the distance from the y-axis on the left-hand side to each point is the same distance from the y-axis to the right-hand side in this particular parabola. Okay, parabolas can also move spaces. It says examine the emoji. Can you see a parabola? Draw it nice and clearly. All right, so I can see the parabola over here. And if I want to draw it nice and clearly, let's see if I can. All right, so I'm going to use a red line, and let's say I try and draw it. So I draw it. Oh, that's not gonna work. Let's try a little bit higher. Here. Oh, still not high. But anyway, it's a bit difficult. I'm going to show the grid, and maybe I'll use this thing here. No, that's going to be a straight line. Curve. Anyway, ideally, if this was perfect, it would be somewhere there. Anyway, whatever. Right, let's just check the answer. Okay, that's how it's supposed to look, like that. Okay, right, you can draw that. That's a parabola. Examine the sombrero. Can you see the parabola over here? You can see the parabola is basically, that can be a parabola. We have another parabola over here on top. We can also have one at the bottom here, one above the orange as well. Okay, so parabolas do exist in the real world. There we go. There's two parabolas. Okay. On the animated image below, draw flight path of the ball as a parabola. Simply, easy, quite just simply draw it like that, right? So there's some kind of line that you have to draw in here. It would end up looking like this. Okay, so there's the drawing, something like that. And you have a parabola to look at from there. A linear graph looks like a straight line. So a linear graph looks like a straight line, or does it look like a circle, or does it look like a shape? So a linear graph looks like a straight line. We know that. Sorry, and what does a parabola look like? So definitely not a straight line. Linear is another word for straight. Parabola, we know, looks like a U shape. It's got some kind of U shape. It's not a circle. It's not a bottomless well. So we know it's a U shape. Okay, let's go to the next one. Drag and drop to fill in the gap below. The lowermost point on a standard parabola is known as this point over here, known as the vertex. All right, and identify which point is closest to the vertex of the 5 labeled points on the parabola. That would be B and D, right? So B and D definitely are the closest points. It says you identify the point which is closest to the turning point, right? The vertex. So B or D, I think, would be correct. So let's have a look at this one here quickly. Oh, actually, I thought they wanted something closer. They actually wanted the vertex. The answer is C. So looking at this one here, that should have been C. C is the vertex. Drag and drop to fill in the gaps below. The x-intercepts, where it cuts the x-axis of a parabola, are points where it crosses the horizontal axis, x-axis, right? Those are your x-intercepts. In other words, for something like this, what you have is you have a parabola. So if I have to quickly just make sure that you understand what x-intercepts are, let's quickly get our x-axis going and y-axis over here. So there's your y-axis, there's your x-axis, and the parabola is drawn nicely, not like mine, and that over there would be your x-intercepts. So what do you have here? You have some kind of horizontal line over there, and you also have a parabola. Okay. Okay, let's move on. And let's continue to the next question. Here is a parabola that crosses the x-axis of the Cartesian plane. There's a negative 1.607, 1.607, you can see that. And the question is asked, identify the number of x-intercepts. There are two x-intercepts, one over there and one over there, where it cuts the x-axis. Okay, those are your x-intercepts. Okay, so now we know what x-intercepts are. It's where the parabola cuts the x-axis. Identify the coordinates of the vertex. Now, vertex, remember, is the turning point. It's right in the middle of our entire Cartesian plane. 0 on the y, 0 on the x, so 0, 0. Ideally, it says please write your answer in that form. So you know you have to write down 0, comma, 0. And then you check the answer. Right. Identify the coordinates of the vertex of this parabola. We can see this vertex is 3 to the right and 2 up. So when we write down this coordinate, it will be 3 on your x, and it will be 2 on your y. And that's where it would turn. So we would write 3, 2 to represent the coordinate. Identify the coordinates of the vertex of this one, 1 and -6. So we then write 1 and -6, and that's where it turns. The y is -6 and the x is 1. So x is 1, y is -6. Alright, identify the coordinates of the vertex of this parabola. We got now to the left we have -2 and we have -3. We have both of them as negatives. -x and a -y. -2, -3. Let's check if it's correct. -2, -3. If it's wrong, let's see if it's not. That's correct, so that's done. So let's keep moving. State in your own words why parabolas are an example of nonlinear graphs. Well, basically, if it's nonlinear, it is not a straight line. It is curved. It is curved. So it can't be linear if it is not a straight line, right? So definitely. Okay. A linear graph is the form of a straight line. Any graph that doesn't, so we could have used the word graph as well in our answer. Okay, parabolas turn up in some surprising places. For instance, objects that are thrown in the air, such as balls or empty cars, they all have a trajectory, some kind of motion in which they move through a parabolic flight path. The path they take through air has a shape of an upside down U. Something that goes up and goes down. If you just throw a ball from one end of the field to the other, and if you kick a ball when you're playing soccer, basketball, if you look at all of the sports, even cricket, every single object that flies up by the law of gravity will have a parabolic shape because there will be some kind of symmetry from where it started to where it ended. So why do you think thrown objects have flight paths shaped like parabolas? Record your ideas in the spaces below. They can be as wacky as you want. You can choose around those ideas, okay? Here's an answer. Objects that are thrown or launched into air are called projectiles, and these are objects that while they're in flight only experience a single force. That force is gravity. Since gravity always acts downwards, it constantly pulls a projectile and forces it lower and lower in the air, even as it travels horizontally away from the launcher. The result is a parabolic path as the projectile curves down toward the ground. This path begins at the point of launch and ends where the projectile hits the ground. You can learn all about gravity and other fascinating forces in science. It turns out that every parabola has its own equation now. And this is where we now move on to some kind of equation. This parabola over here in particular has the equation y equals 0.071 x squared plus 4. And let's discover a bit more of this. The basic equation of a parabola is built on the idea of having x squared. Y equals x squared. So for any parabola, you can write the equation that contains the term x squared. If you see x squared in a function, then that function is representing a quadratic equation, which will, when you draw it, look like a parabola. Here we've got trajectories and we've got changes over here. These will be two different equations, two different pathways at which you can travel. So y equals x squared. This equation says that for any particular x value, if you square it, you'll get the y value. So when you square x, you end up with y. If I take -2 and I square it, I get 4. If I take -1 and I square it, I get 1. If I take 0 squared is 0. 1 squared is 1, and 2 squared is 4. What you notice is that the y value is the same for -2 and 2. It's the same for 1 and 1. And this is how you end up with the curve, starting at 4, going down, going back up. And when you substitute it into the equation, you have to square each of these values to get the corresponding y values. The first provided x value is -2, so we substitute it in, just like I did, and we square it and we get 4. We did that for all of those values. And that's how we get that table. Now we plot this on the Cartesian plane. Looking at each column, we can extract this 2 points as a coordinate. We can take out -2 and 4. We can take out -2 as your x and 4 as your y. -1 is your x and 1 is your y. And you can continue like that. Alright. Each pair of values gives the location of a point on the Cartesian plane. Let's have a look at -2 and 4. Go 2 left and 4 up. So you're plotting the point -2 on your x, 4 on your y, and that's your first point over there. And if you go -1 and 1, you get -1 to the left, and 1 up, and then you end up over here. Then you've got 0, 0, 1, 1, 2, 4. Exactly the same on either side, right, of the equation from there. Okay, now let's go to the next one. Avoid drawing straight lines between adjacent points, it says. So you don't want to connect it using a straight line. It has to be curved. Curve is very good, okay? And it says, if you like, you can draw arrows on the ends of the curve to show that it extends forever. So you can put some kind of arrow on both sides of the curve, one on this side and one on this side as well. Okay. Mark these 5 points on the Cartesian plane, it says, and join them up to form a parabola. So let's have a look at this. The first point over here is 2 left and 3 down. So -2 and -3. So we're going to make a dot, go -2 on the x, -3 on the y, and let's make a dot there. Then we got the next one, which is -1 and 0. So x is -1, y is 0. The next one is x is 0, y is 1. The next one is x is 1, y is 0. And it's basically just exactly the same as the first one, reflecting it on either side. And that gives you basically the graph once you connect the dots. Let's plot the next one. You got -8 and -6. So -8 is over here, -6 is all the way down here. Make a dot. So we're done with that one, right? -6 and 7, -7, -6 and -7 is over here. And then you've got -4 and -6, -4 and -6, which is over there. And then -2 and -3, -2 and -3, which is over there. And 2 and 9. So these are very random. They're not particularly all symmetrical. And you can see that from there. Just erase that one. And there you go. That's the points. This parabola is going to be slightly off the page, but the turning point is at -6 and -7. Let's see if it's correct. Let's have a look at the answer. Oh, that was that one, previous one. There we go. And you can see that's the parabola, and that's how you would sketch it. So from here, we then move on to the next type of equation. After we've done that, it says here, this parabola now is described by the equation y equals x squared minus 5. So after we've squared x, we have to minus 5. So what is -3 squared? 9. And what is 9 minus 5? 4. That's how we get 4 here. Then we take -2, substitute it into x, square it, becomes 4. 4 minus 5, -1. -1, substitute it into x, square it, becomes 1. 1 minus 5, -4. Take 0, substitute it into x, square it, minus 5 becomes -5. 1 squared is 1, minus 5 is -4. 2 squared is 4, minus 5 is -1. 3 squared is 9, minus 5 is 4. And you can see there's some kind of symmetry. 4 and 4, -1, -1. 4, -4, -4, and -5 seems like the point at which it would turn. So I now plot this. So I go -3, 3 to the left, 4 up. Let's start from the center. Let's go 3 left. We go 4 up. Place a dot there. Then we go 2 left and 1 down, apparently. So it says -1. You can see that there. The next one is -4 and -1, right? So -1 to the right and -4 all the way down. The next one is -5. And then you can see there's some kind of symmetry involved in this. The last one is 3 and 4. And we end up with that kind of parabola, which we connect the dots for. Alright, there's some kind of substitution, the calculation you can see. By changing x into -3 and squaring it, you get 9. 9 minus 5 gives you 4. Alright, don't worry about the BB. Alright, so it's just 4. The next one, the squaring only happens after you've minused it. So in this kind of parabola, they haven't squared out the brackets. So you could write the brackets twice and square it out, or you could just substitute directly into it. So if I take 3, 3 minus 6 will give you -3. And -3 squared is 9. So I know this will be 9. And then let's take 4. Let's take 4, put it in x. 4 minus 6 is negative 2. Negative 2 squared is 4. 5 minus 6 is negative 1. Squared is 1. 6 minus 6 is 0. 0 squared is 0. 7 minus 6 is 1. 1 squared is 1. 8 minus 6 is 2 squared is 4. And 9 minus 6 is 3 squared, which is 9. And we end up with this parabola. We again plot these points again. And you end up on this side. You can see this parabola is moved from the middle line, where now you can see it is reflecting over this line. And this line is normally called the line x equals 6. And it's a reflection over the line x equals 6. We'll see that as well. Okay, a parabola is described by the equation y equals 9 minus x minus 1 squared over 4. A more complicated form of the parabola, but the same rules apply. Take the number, substitute it in, square it, divide it by 4 after you've squared it, then take 9 and minus it. Let's see if I can do this in my mind. Negative 7, I put it in x, I get negative 7 minus 1. Negative 7 minus 1 is 8. Then I take 8, negative 8, and I got negative 8 squared is 64. 64 divided by 4 is 16. And 9 minus 16 is negative 7. Hold on a second. 9 minus 16 is negative 7. Let's just check. Negative 5 becomes negative 5 minus 1, which is negative 6 squared, which is 36. 36 divided by 4, it'll give you 9. 9 minus 9 is 0. So this is 0. Put negative 3 in there. Negative 3 minus 1 is negative 4. Negative 4 squared is 16 divided by 4 is 4. 9 minus 4 is 5. 1 minus 1 is 0. 0 squared is 0. 0 divided by 4 is 0. This whole thing will become 0. And then 9 minus 0 will give you 9. Take the 5, put it in there. 5 minus 1 will give you 4. 4 squared will give you 16. 16 divided by 4 is 4, and 9 minus 4 is 5. We're back to 5 again. If I take 7 minus 1 is 6 squared is 36. And 36 divided by 4 is 9. And it becomes 0 again, right? And then 9 goes into there, becomes 8 squared, which is 64 divided by 4, which we said was 16. So we end up with negative 7. All right. Now, this is what we need to plot. So we plot the points carefully, and you can see the numbers. The y values are getting more and more and more and more and more. Up till this point, then they're going less and less and less and less again. So we're looking at some kind of sad-faced parabola. Let's have a look. There we go. We plot the points, and we end up with that. The turning point is at 1 and 9. And you can see there's all the other points plotted from there. Remember x first and then y all the way through. All right, well done if you made it through to this first lesson. Now it says a parabola is a type of nonlinear graph. Let's recap how it works. Remember, we can move this around, okay? And one of the most important features of the parabola is the vertex, and that's the turning point. In this case, the turning point is 0, 0. And in this lesson, you had to identify the vertex and plotting parabolas from a table of values. Okay, you can see there we go. And we connect it from a table of values. You also learned that parabolas can describe quadratic equations, and they have some kind of equation form or the other. Okay.